I'll turn it over to Stephan. Talk about robust deep learning.
Great. Thank you so much for the invitation to speak. As you mentioned, I used to do theoretical physics and math, and I switched to machine learning a couple of years ago. So today what I wanted to discuss is some research that I did during my PhD on robust deep learning. And it's still work that is sort of ongoing now. And just to give a sort of introduction to the problem, here's like a sort of canonical example of the uses of deep learning today in the lab. So there's this well-known data set, the ImageNet large-scale visual recognition data set. And in this data set, we have all these kinds of images of this animal here. This is a fawn, right? So we have this high-dimensional image X, which sits in some vector space R to the D, where D is like the number of pixels in this image. And then we can apply this neural network function to it. And this is sort of a diagram of something that's called GoogleNet. GoogleNet, that was like the sort of state-of-the-art image recognition neural network a few years ago. And then at the output of this neural network, we get a vector here, which is like a vector of probabilities. And what people have shown is that if you have like this really big data sets, then we can train these neural networks such that their probability vector, for instance, here has like the highest probability at the right class. So this is a fawn. That's this animal here. So I can't always see everyone's or can't hear everyone's like response. So please stop me if I'm not clear about anything. If you have any questions. Okay, so here's like it was a very like common, very simple application of deep learning. But obviously, in the real world, like it's much more complicated, right? So if we want to apply deep learning to self-driving cars, for instance, and we want to recognize images or objects in images, then things are not as nice and sort of isolated like the fawn in the previous picture, but there will be a lot of noise and a lot of confounders in the image when we try to do image recognition tasks. One of the recent developments that people have been sort of working on is solutions for the problem that neural networks are actually very easily fooled. So people have shown that if we take this image of this fawn, some noise to it, then it's very easy actually to make this neural network think in this case that that now the arc max of this probability vector goes to monkey, right? We add just a little bit of noise to it, we can drastically change the answer of the neural network. And this is actually not just like restricted to images. For instance, for audio. So this year there was like a paper by Nicholas Carlini, and he basically showed that if you take an audio waveform and you apply this neural network to it, for instance, it can learn to transcribe this audio waveform. So it says this was the best of times, it was the worst of times, but then we can find this very sort of like peculiar noise pattern overlaid on top of our original waveform. This doesn't actually change the global shape of the waveform, but the neural network then outputs a completely different sort of transcription, very different from the original transcription. So this is a big problem. So we can add this imperceptible noise to our high-dimensional input, and we can easily fool the network, even though as humans, we would not see or hear any difference between these inputs. So in general, this leads to this like this technical issue of what robustness means, or what we want to achieve. And so robustness, let's say I have an image X like this fawn here, then what I would like is for all inputs x prime that are close to x. So d is some Euclidean distance, for instance, and I have some parameter delta. Then I want the outputs of the neural network onto these two inputs to be similar as well. So capital D here, we can think about this as like some distance measure on these probability vectors. This is sort of a formalization of the idea that if I have these two images that are very visually similar, then their outputs hopefully are also quite similar. And it turns out that actually there are many perturbations. So from x, we can add many perturbations dx to basically actually make this, to violate this sort of robustness property. And so in natural, sort of in the real world, even on the internet, for instance, things like image compression, cropping of images, rescaling of images can actually cause these kinds of problematic perturbations. And then secondly, there is a very active sort of research area now where people try to come up with sort of algorithms and formulas to construct clever patterns of perturbations such that you get these kinds of errors. Okay, so today what I wanted to discuss is two papers that basically try to do something about this problem. The first one is called stability training. It's one that I was working on at Google 2 years ago when I was an intern there, where basically we come up with a very straightforward technique to get robustness against natural perturbations. And in the second paper that we worked on last year, or ongoing, I guess, this is work that's called neural fingerprinting, in which we try to detect adversarial text. So that there's like these sort of crafted perturbations. So before I dive into the first work, are there any questions so far about this? So I don't hear anything.
No questions, I think, from here.
Okay, great. Okay, so then I'll just go to the first work. So the first book is called Improving Neural Network Robustness via Stability Training. So this is work with some people at Google, and this was published as CVPR in 2016. And so here, the practical problem is that Google uses these huge neural networks that I described earlier to do things like not just image classification, but also image similarity sort of matching. So the way that works is that you can have two images and you can ask, are these images the same? And then it turns out that these two flowers here have a very small visual difference. These two images have very small visual difference as well. And then the way you check if these are actually similar is that you can take the features, which are the output of the neural network at a very high level. You take the features of image A and image B, and then you compute their distance. And it turns out for these two images, the distance is 0.008, and then here's 0.1. But it turns out that if you take these very visually dissimilar images of these plants here, then actually the difference here in feature space is smaller than the difference between this pair in feature space. And so this plant here actually looks more similar than this pair of images, the blue ones in the middle. So this is a very another example of why neural networks are actually making a lot of mistakes that are not very natural. So what is a very simple approach? So as I said before, is that you just want your network that as an input X to have similar output on X plus some noise. And so why don't you just directly train on this, right? So the objective that you can try to minimize is to take the Euclidean, the L2 norm of the distance between the output of F on X and on X prime, and you basically sample a lot of X primes, or maybe all of them, and then you just try to like train your neural network to minimize this Euclidean loss. And so we can think of this as doing a form of regularization of the neural network around this input X. Okay, so the idea here is actually quite straightforward, but there's like two like subtle points here. So what we do here, if we add this like stability objective, we basically have like the original classification loss, for instance, or image similarity matching loss, and then we add in stability training, we add like the stability loss to the total training loss. So when we train a neural network, we have this sum of these two losses. So the difference here is that we force the network to behave similarly on these perturbed inputs, even if the network is actually wrong about its prediction on the original input, or on like if it's actually wrong on the X prime here. So that is actually a subtle difference with what you might do using data augmentation. So what you do during training is that you basically get an input X here. So that this input is given to you, and then you add a bit of noise to every example to get this X prime or I prime in this diagram. Then both go through like this neural network, and then you basically get two outputs of this neural network. So your original classification loss is only computed for the original unchanged image, and then you just regularize the network to be similar on the original plus the augmented image. So this differs from traditional data augmentation, where you, for instance, would compute L0 on both the original and the noisy image. So a slight difference there. And the second point here is that you basically sample these X primes. We sample the noise as like a Gaussian during training, and every step during every forward pass through the network, we sample one of these DXs, IID from this Gaussian. Okay, so this is quite simple to implement. It's not very complicated, but it turns out that this is actually like very effective, as opposed to what happens when you actually use data augmentation, where you just add these X primes to your training data set, but only use this original loss L0. So how does it show itself? Well, it turns out that stability training improves the near duplicate detection precision recall rate by 2 to 3% on corrupted images. So for instance, let's say that you take images that are originals, and then you take the JPEG version of those images. And the question is, can you detect that these images are actually the same? Now, if you look at the baseline here in blue, you see this was basically the state-of-the-art Google neural network that Google used back in 2016. And then if we add this very simple stability training loss and training procedure on top, we get this very clean 2 to 3% improvement in area on the curve on this precision recall graph. Something similar happens if we look at images and random crops that we take out of that image. So the random cropping also causes some very slight perturbations in the input to the neural network. And we see that similarly, like if you use stability training, then the neural network improves its similarity detection by 2 to 3% on these types of data. And so because this actually represents quite a big gain, so improving 2 to 3% on the state-of-the-art system is quite significant, well, definitely for Google. This is now deployed in Google image search because image similarity is basically used to do image retrieval within Google image search. Similarly, if you apply stability training, you can actually improve the classification performance of these Google networks by a significant margin on corrupted images. So here we see in this graph what happens if we basically take clean images. So for horizontally, there's the quality level under JPEG compression. So 100% is basically the clean original image. And as we go to the right, the image becomes of lower and lower quality. And we see that basically these four curves all represent different neural networks. And as the quality decreases of the image, the classification accuracy of these neural networks decreases from about 76% to roughly 65%. Now, the baseline here is in blue. So this is like a state-of-the-art image recognition, image classification network. And then in red, yellow, and green, we have networks that have been trained with stability training with different hyperparameters. So sigma here is like the standard deviation of the noise that gets added to construct our X prime during stability training. And what we see here is that these networks, their performance around like on the clean data set is quite similar, but they have a much more graceful decline in performance as they are being applied to images of worse and worse JPEG quality. So for instance, here, like, the difference between the green and the blue line is like, around 5% on like these low quality images. Similarly, if we vary the loss coefficient alpha in front of the stability training loss term, we see that we similarly see like a much more graceful decline towards like the low quality images. And again, for Google, this is like quite significant because in reality, again, like, in the lab, we can test these neural networks on clean images that are here at 100% quality level. But in reality, like when Google is scraping the internet, it sees a lot of images where the quality level is actually quite low, in the order of 50 to 20%. And those that 5% gain that you get from stability training is actually quite significant for Google. So that was like a very short sort of segment about stability training. Is there any question about this particular part?
We do have a couple of questions from here.
Yeah.
Hello. So, recently, a couple of months before, this invertible deep neural network, that concept was proposed. So how do you compare your CBPR 16 paper with this idea where CNN is invertible so that the image can be reconstructed from the last layer of the CNN?
Oh, I see. Yeah, like they're like sort of autoencoder type, I guess, like networks. Yeah, I think that we haven't tried doing that, like, using denoising autoencoders and similar constructions. I'd say that that's sort of complementary. Like, you can definitely like add stability training to that as well. This is 2 years ago, so we didn't do experiments with that back then. Mm-hmm. But the thing is with these denoising autoencoders that they are still susceptible. Like, they don't solve the problem completely of being robust to adversarial perturbations. Mm-hmm. Yeah. So, but I don't know exactly when you combine it with stability training, how it would do. Yeah.
Oh, okay. I have one more concern. Say, for example, you are training your network to learn that a small difference which is represented by dx. So network will learn to differentiate this from the original x, right? Which is your image. Now, if you look at that, the original concept of CNN, that it has the ability of generalization, right? So, mm-hmm. but now if we train the network to differentiate between x and x plus dx, don't you think that the very purpose of CNN will be lost in the for many applications?
If I understand the question correctly, is that you're concerned that if we over-regularize these neural networks, then they basically don't see the difference anymore between dogs that might be very similar?
Right.
For instance?
Right.
Yeah, so I understand the concern. I think that, so in these high-dimensional spaces, I think it's good to keep in mind that, like, even though we are sampling from this Gaussian ball with, let's say like standard deviation 0.04, right? That represents a very, very small volume in this high-dimensional pixel space, right? So in reality, if you think about what stability training is doing, it's only enforcing this sort of smoothness of the neural network on a very small area around every natural image. So if you actually compute the distance between, let's say, two dogs in the ImageNet data set, right? Or even like two dogs that are slightly rotated, their distance is much bigger than the typical like XX prime pair that we use during stability training. So there's a significant gap basically between two images in a wild, so to say, and like the images that we, the perturbations that we apply during training. So I think that I'm personally not that concerned that like this is going to destroy like the performance of these neural networks on real image data sets anytime soon. Maybe that's a short answer.
Okay, thank you so much.
I was wondering if you could comment on the difference between this method in performance and that of like adversarial training more directly, and whether this method could be improved by adding an adversarial training aspect.
Right, yeah, so in adversarial training, I guess, I will get to the next part, I guess, when I actually talk about adversarial attacks. Certainly, I guess, like in that context, like, you would add JPEG images to the training data set, for instance, if we want to become robust to JPEG perturbations. We did try that, basically. So the thing with that is that you will certainly become more robust against JPEG perturbations, but you might not necessarily become more robust to, let's say, perturbations that come from cropping the image. So basically, the nice thing about stability training is that it gives you robustness to all these different types of real-life perturbations that we tested on simultaneously. So there's one model that becomes robust to all three of these JPEG perturbations, cropping perturbations, and rescaling perturbations. So that's one difference. But data augmentation with JPEG images definitely helps. Yeah.
Can you give us some intuition on why augmentation would not work, but stability training would work?
Yeah, that's a good question. If you do straight up data augmentation, this is just an empirical statement. I don't have any theory to back this up. But as I said, sometimes like these, if you look at the top performance of these networks, they still make mistakes, 20% of the time, for instance, like for these original networks, right? The top one classification error rate is still about 25%. So it means that basically also that the network most likely is also gonna like make a mistake on X prime. It makes a mistake on X, it also makes a mistake on X prime. Now, it just so happens empirically that it gives us much worse performance, like, in terms of robustness, if we include the loss on X prime as well. My personal guess is that basically somehow the gradients from those examples have a very bad, like, they tend to sort of, the kinds of smoothness, I guess, they induce in the network is somehow not the same. That sounds a bit vague, but I don't have a clear, like, theoretical explanation right now of why that's true. It just happens that empirically we saw this over and over in our experiments that this is true.
To extend that a little bit, I'm sorry, I don't know how much time we have. Would it be fair to say that augmenting the loss the way you have done it, you kind of ensure that you are not losing performance on the unperturbed data? Is it a more explicit way of doing it? Is that why maybe the performance doesn't, is that why maybe the performance is better than just throwing everything in?
Yes, I agree with that statement. I'm just not sure how I can put that on a solid theoretical foundation right now. Okay, I didn't hear the last part, but I assume that was not a question.
Thanks.
Okay. All right. Okay, great. So the second work I want to discuss is called Detecting Adversarial Examples via Neural Fingerprinting. So let's go back to our fawn example. So now the question is, if like an adversary is going to like purposely like find a dx to construct an x prime that's going to fool our model, can we detect that? So for example, let's take our fawn picture here. What I would want is like an algorithm that says, okay, this is what you say about this image. Like, you say it's a fawn, and then we conclude it's not adversarial. But now there's like a very clever adversary that's going to add this sort of perturbation, a very small one, right? So we can definitely still say it's a fawn, but now the network says it's a monkey. And now what we want to say is that, oh, stop, like, somebody messed with this image, right? Somebody, definitely purposely tried to include this perturbation. So how could we do this sort of detection task? Now, what is sort of like the role of the attacker here? So an attacker, let's say that you have some input x and a label y, some loss function L and some model parameters theta. Then the attacker basically wants to find some x prime, which is x plus dx, such that it basically maximizes our loss. So it tries to find some x prime that, like if I look at x prime and like the answer of the network, and I compare the answer of the network with the ground truth label y, then this loss gets maximized by this example. But at the same time, the attacker typically wants its x prime to be close enough to the original input x. And the role of the defender here is to try to find some mechanism or some good solution theta that ensures that no solutions x prime exist within some distance delta of my original, my clean data x, or at least, if there is some solution, at least, tell the user that, somebody's trying to mess with the network. So starting from 2014, when people sort of like started doing this, these types of attacks, there's been a sort of ongoing arms race where if you look at the literature, many attacks and defenses have been proposed, but also many defenses have been broken because people just came up with smarter, stronger attacks. And it's very hard to find some sort of theoretically guarantees on the robustness in these kinds of attack scenarios. So just to give you sort of like an overview of what people have been doing in the attacks, along the attacks dimension, sort of I think the first paper that sort of pointed out this issue and sort of came up with a very simple way of constructing an X prime was Ian Goodfellow back in 2014. So he proposed something called the fast gradient sign method. So the idea is we just take X, we take our loss function L, we take a derivative with respect to the input X, then we take the sign of this derivative, and then we add like, epsilon, where epsilon is a small parameter, and we add this noise pattern that we find added to X. And in the years after, people have come up with iterative versions of this by Alexei Kurekin in 2016, projected versions of this by Madri, saliency map approaches, and sort of the strongest attack that people that exists today is the so-called Carlini-Wagner L2 attack that was published in 2016, in which basically people solve this sort of constrained optimization problem where we try to minimize the p-norm of this perturbation dx, and then we have a sort of function f. This f is not my neural network f, it's some other f. I apologize for that. But you basically choose f to be a proxy for misclassification. So So if the predicted class C of this x prime, which is x plus dx, is some pre-specified class that is not the original class, then this f is less or equal 0. And so we assume it's not so hard to like come up with these functions that satisfy this property. And this attack basically is very powerful in the sense that it can find perturbations that are very, very small among, compared to all the other attacks, but it's really slow. And there are also some other attacks, such as the SPSA attack, which is actually gradient free. It doesn't use these kind of DL/DX or variations thereof. Now, on the side of defenses, there's been a number of works. I won't go for all of these like in detail, but roughly speaking, you can like put them in 2 buckets. One is robust prediction. So in robust prediction, people have tried to come up with convex relaxations of neural networks. Again, trying to sort of smooth out like the neural network so that it becomes less susceptible to like small perturbations. Coming of non-differentiable nonlinearities. The idea there is that you can basically frustrate the attacker that tries to compute DL/DX, and then GAN type approaches where you denoise images again to try to filter out the small perturbations that the attacker might have added to your input. And on the robust detection side, in some sense, you have a slightly easier job. Your job now is just to say, like, is this a real image or is this an image that her has crafted for you? And in this sort of like the most relevant works were this paper by Ma from this year, basically based on something that's called the local intrinsic dimensionality, where it basically tries to compute a sort of geometric quantity associated with your image, sort of measuring the local curvature, if you will, and then, based on that, seeing if whether or not your image was real or not. But I have to say, sort of the short summary is that most of these attacks basically have been broken already by, basically people that came up with stronger attacks. And it turns out that all of these defenses can be circumvented in some pretty straightforward way. Okay, so here's our sort of proposal, our like, latest, battle in this ongoing arms race. And so here's the idea of neural fingerprinting. So let's for now assume that we somehow have chosen some sort of fingerprint where I'm going to define a fingerprint as some input perturbation delta x. Now this is a capital delta and a delta y, where delta y is some sort of specified output change that I want to see. Now, what neural fingerprinting does is sort of a local consistency check. It says, on some given input x, I'm going to check if the model behaves as expected. So what does that mean? So let's say I have this image x, I compute the output of my network. So these are, again, the class probabilities. Then I apply my chosen delta x to this image. I can compute the output of this neural network on this x plus delta x. And then I compare. I compare like the 2 outputs and just see if they match my chosen delta y. And now assume that I have some like collection of these guys, and I can just see, is there any delta y that matches the output of the network? Now the idea is that like if there is such a if there is some match, then I'm gonna say that this image is actually okay. If there's not, then X apparently is adversarial, because the network does not respond in the predicted way around this input. So this intuition basically is, like, okay, well, we can just do this local consistency check. So instead of having just one delta x, now I can pick n directions delta x. And now for if I have j classes, so let's say, for image that I have 1,000 classes, then for every class, I'm also going to choose some delta y's. And the intuition is that it actually becomes increasingly hard for an attacker to find some adversarial perturbation dx, this is a small dx, that actually conforms to the whole collection of secret fingerprints. the fingerprints can be secret or they can be known. So we'll discuss both cases. But the idea is that this conforming to this prescribed fingerprints, it becomes very, very hard. So I have this image X. I apply my chosen delta Xi's. And then basically what I'm going to compute is basically I'm going to look at the difference. So the difference of F on X and F on X plus delta X. And I'm going to check whether this difference conforms with any of the delta Y's or collection of delta Y's that I've chosen. Okay, so how do you train a network to do this? So you basically train a network to behave according to the fingerprints on real examples. So if I'm training a network, I have my original classification loss, let's say, and I'm going to add this fingerprint loss. So now again, we assume that we somehow obtained this delta X and delta Y. I can add this sort of regularization term, this fingerprint loss, to my training loss, and then just do standard gradient descent. So a small detail here is that if you train, you only use the fingerprints that were chosen for the ground truth class of this input X. And then during detection, what you do is here's based on algorithm box. We can define like this distance measure as before. Now let D, we call it D. So it turns out that actually what we do in practice is that we take the normalized logits. So the logits are the output of the layer just before we compute class probabilities. We take normalized logits. We look at the difference of these logits on the clean and the perturbed inputs, and then we compute this this distance D. And so in this algorithm box, you see how neural fingerprinting works. So just to reiterate, we get some input X. We have all these fingerprints that we've chosen, and we also choose some threshold value tau. And we basically just check whether or not there's some class J for which this distance is smaller than our threshold tau. And if that is true, then we accept this input and we say it's real. And if not, then we reject it and we say that this input is fake. One detail I didn't really talk about so far is how do you actually come up with delta X and delta Y? And what we did is basically you just randomly sample. So before you start training, you sample your delta Xi, just as, again, in a Gaussian ball, and then you choose your delta Y ik. So delta Y is a vector. Here L is like the index for this vector. And so for every fingerprint direction I, and then basically let's say the ground truth class is K, then we basically randomly flip a coin and say that delta Y should either be negative or positive according to these parameters alpha and beta. Okay, so here's some details. I think I probably don't have too much time left, 10 minutes, 10 minutes maybe. So I won't skip, go for all the details. But basically the idea is that we just randomly sample these delta X and delta Ys before training, and then we fix them. And then the good thing about this is that the random sampling means that we assume very little, basically, and we give minimal information to the attacker about any sort of bias that we might have introduced because we, try to be clever about choosing delta X and delta Y. And again, the attacker might or might not know the chosen fingerprints. So actually, if you think about this, you can actually show that for linear models, it's kind of easy to understand what happens if you use this procedure. And in particular for an SVM, you can show that there's actually, with just 4 fingerprints, you just maximize the regions of adversarial examples that get always detected by these 4 fingerprints. So for binary classification, this fingerprinting mechanism just detects whether or not the predicted class, which is the sign basically, is correct. And it turns out that you basically can detect any adversarial examples that is basically too close or too far away from the data distribution. So if you have negative examples here in red and positive examples in green, and we have this brown decision boundary of our linear classifier, then you can basically choose these purple fingerprints. So here I'm only showing 2. But you can choose these kind of purple fingerprints, and they will exclude all the light blue examples that would be in adversarial. And the intuition here is that, for instance, if you look at the delta x1 here, if you compare basically the behavior of the linear classifier on the any red negative example, and any example that you get by adding this delta x1 to it, you see that any other example will always will still be below the decision boundary. And so delta x1 should not see any change of the predicted class between x and x plus delta x1. But if you're basically too close to the decision boundary, then x plus delta x1 suddenly will see a change in the predicted class. So delta x1 basically detects all these adversarial examples that are too close to the decision boundary. And similarly, you can draw similar fingerprints for the other regions. Okay, so turns out that you can do this for linear models, but what actually happens for nonlinear models? So if you train a neural network on, again, a binary classification, but now you high-dimensional image input. So just to remind you, the fingerprint loss was train a network to conform to the chosen delta x and delta y's, then you can visualize what happens. So here's the picture without neural fingerprinting on the left here. So on the left, you see that the neural network learns to behave more or less like an SVM. So blue here is a region that belongs to class 1, or that the neural network thinks should be class 1. Yellow is for class 2. And once we introduce these red fingerprints here, we see that the decision boundary that the neural network learns becomes drastically different. And particularly if you look at the fingerprint loss in the panel on the right, you can see here that like dark regions are very low fingerprint loss, and then any white and gray regions are very high-ish. You see that the fingerprint loss is its minimum very tightly around the real data, and outside of the real data, this fingerprint loss quickly becomes higher than the dark region. And so it is easy for us to distinguish between the real data and all the regions that are not sort of the real data by looking at this fingerprint loss. And ideally, if we want to properly detect all adversarial examples, the fingerprint loss should be should have its minimum, let's say, on the real data, and be always provably higher outside of the real data. Okay, so this is sort of like a visualization of what happens. And now I wanted to talk about some experimental results on real life big data sets and real proper big neural networks. And so before we go to that, I want to talk a little bit briefly about the different security scenarios that people consider. And so just to set some terminology, neural fingerprinting, as I presented, is the so-called black box defense, because it doesn't actually assume anything about how the attacker might try to construct this DX to try to fool us. Furthermore, we can evaluate neural fingerprinting in different attack scenarios. And so basically, there's a distinguish, we can make a distinguishment between its theta and whether the attacker knows the delta X's and the delta Y's that we've chosen. And depending on this, we're either in a black box, gray box, or the adaptive white box scenarios. Depending on the sort of papers and the community you go to, you will see different terminology, but this is for our purposes today. We'll focus mainly on the gray box and the white box setting. So what that means in practice is that, for instance, in adaptive white box evaluation setting, when we construct adversarial examples, we basically have to solve the following optimization problem, where we minimize the distance between the X prime and the original input X. We have some loss that promotes misclassification. And then we also have our neural fingerprinting loss, because the attacker has to make sure that he does two things. The attacker has to maximize my classification loss, let's say, but he also has to make sure that it passes our detection mechanism. And for that, it needs to make sure that this fingerprint loss is actually very small. And I realize this minus sign should be a plus sign here, so I apologize for that. But we should, or gamma 2 is negative, but I hope that I made clear what we want. We want this LFP to be small and this LCW to be big, let's say. Okay, so here's the setup. You basically sample some fingerprints. You train your model to have a high task accuracy and to have a low fingerprint loss. And then on the test set, you are going to generate adversarial examples for images that are correctly classified. And then you check how many basically images that are real, so real test images and adversarial images are correctly detected by this neural fingerprinting business. Okay, so I'll come back to this later. And so there's some sanity checks that you should do, but let's first go to the sort of experimental results. So in a gray box setting, where the attacker doesn't actually know what the fingerprints were that we chose, we basically get near perfect detection rates on all of the state-of-the-art attacks. So if you look at MNIST and CFAR and Mini ImageNet, and you basically try to construct these adversarial examples using the fast gradient sign method, the Jacobian saliency map, the iterative attacks, the Colleen-Wagner attack, basically neural fingerprinting gets near perfect detection rates. So near perfect detection rates means that you get 100% area under curve under the ROC curve, and basically neural fingerprinting gets close to 100% in all of these data sets and under all attacks. And you can see for comparison that if you look at the baselines like LID and all the other methods, they basically start to break down as the attacks grow stronger or as the data sets become more complicated. And even in fact, like if you look at ImageNet, these defenses just don't scale anymore. They just become so slow that nobody can actually evaluate these defenses. So here's like a visualization of the ROC curves. You can see for MNIST and CFAR, basically if you plot the true false positive rates, we're very close to perfect detection. Now, if we go to the adaptive white box attacks, in this case, the attacker actually knows which delta X's and delta Y's we chose. You can see again that if you take the attacks as is and you train them on the loss function, which includes the fingerprint loss, then still these attacks have a very hard time. So we ran these attacks for many, many iterations. So basically we give a lot of computation time to let these attackers find the solutions to the optimization problem that I presented earlier. But still, at the end of the day, neural fingerprinting has almost perfect detection scores on these adaptive attacks as well. So just like one sort of note here is that you have to be very careful when you do these kinds of evaluations. So part of the game here is that if you run these attacks, you have to tune the hyperparameters of these attacks very carefully and give a lot of, do a lot of sort of binary search over the possible settings of these attack parameters and let them run for many, many iterations. But basically, these results represent about a month in GPU time, and it turns out that we can still detect these guys really, really effectively. So it turns out that also if we vary the hyperparameters of neural fingerprinting, so for instance, we change the magnitude of the delta X's that we sample, then the performance actually doesn't decline too much. So here we plot the area under curve as a function of the delta X's norm that we pick, and also as a function of the number of fingerprints that we pick. So for instance, here on MNIST, you can see that if I only chose 2 delta X's, then basically I would get an area on the curve of anywhere between 50% and 100%. But as we increase the number of fingerprints from 2 to anywhere beyond 5, we see that the area on the curve basically jumps up to close to 100%. very quickly. And it tells us that basically neural fingerprinting, even with a small number of delta X's and delta Y's, empirically is very effective. It very quickly learns to detect like the strongest adversarial attacks that we currently have out there. And this pattern is similar for CFAR, although here, like at the left, I guess, in this plot is not as pronounced as here for MNIST. So just to sort of like conclude, one thing I sort of skipped over is basically a number of sanity checks that we did that you have to do, that's been accepted in the community as sort of like a sanity check for your detection. One of them involves basically trying to break your own defense. So this is something that's some sort of an ongoing battle. So I think I don't have much time left, but I'll just like summarize these slides by saying that we passed the sanity check, so to say. And then I'll just like summarize like what neural fingerprinting is doing. So hopefully what I sort of showed you with the previous empirical results is that neural fingerprinting is a very promising basis for the defense of neural networks. It's easy to implement. It's easy to execute. Right now, it gives a state-of-the-art detection of adversarial examples. It works very well in both the gray box and the white box settings. And it shows us that the current attacks are basically not strong enough. And also, we pass sanity checks for these kinds of detection mechanisms with like a small caveat. Basically, we have to invent a new attack that has not been published yet to break our own defense. So where does it bring us? So in the future, there's like some ideas that we have to extend this fingerprinting defense to further improve the detection rate and robustness against the stronger attacks. We'll develop stronger attacks. That's part of the game. But in the end of the day, we really want to have some sort of theoretical guarantees and stop this sort of silly arms race, because obviously we cannot go on like this forever. And so for instance, what we want to know is there a way that we can, for instance, guarantee that the fingerprint loss will always be bigger than some threshold, let's say for X prime that are within like some distance delta of clean data? Or is there some class of neural networks for which we can prove such bounds? Because if we can do that, then we can theoretically guarantee that neural fingerprinting will always be able to distinguish real from adversarial examples. And finally, that sort of brings us to like me, at least to like a personal interest of mine. I apologize for this, I'm a bit cold. But what we really want to do is we want to characterize the loss function geometry of neural networks. Because if we want to understand how we can bound the fingerprint loss from below, then really what we need to have is like a better understanding of what the curvature looks like of these kinds of loss surfaces. And that is a wide open topic for research. So I hope that I've convinced you of sort of that neural fingerprinting is very promising. And I'll close with just thanking my collaborators, Hee-Sung Yeo, who's a professor at Caltech, and Sumanth Defadri, who's like a PhD student. He's really good. He's at Caltech right now. And Yang Song and Ian Goodfellow, who are at Google. And that was it for me. And I realized I went over time. I apologize for that.
So thank the speaker. Any questions?
Hello. So I have one question that say fingerprinting, your fingerprinting technique considers delta X at the for the input. Now, what happens, say, if I start with a natural image, which is very different from X, say, probably X is a image of fawn, and I started generating adversarial image, say, image of a road sign or something. And then, since, say, I mean, could be a white box or black box attack, I generate an image which is classified as the class of X. So in this kind of adversarial attack, So how this fingerprinting technique would give some safeguard against this kind of attack?
Right. Yeah. So what we hope is that fingerprinting has like made the network behave in a certain way around the real data distribution. Right. So if I've an image of this font, then I want the network to behave in a certain way around like pictures of fonts. So if you give me a picture of this square root, then the working assumption here is that the network locally behaves very differently around this image of a square root. So even though it might classify the square root as a font, what we're assuming here is that the local behavior is very different and that we can detect that using neural fingerprinting.
But by local behavior, what do you mean? I mean, which part of the network will give you a signal that this is a very different image which will have the same class level?
So we don't rely, I guess, necessarily on the class label by itself. So we chose these delta x's, right, as a sort of direction to check. So when we choose these delta x's, we say, you give me this image of the square root, right? We add this delta x to this image, and we see how the network responds. And then we just look at how the response changes. Like class prediction could be completely wrong on this square root image.
But if you can go to your slide on loss function, is there any scope for doing this, of checking this part?
Yeah, for instance, here the fingerprint, if you look in the in this neural, the LFP, let's say you have a new image X, right? And then I can like apply my delta axis to it, and I can look at the change in the function, and we can look at the change in the response of the neural network. And I check that against my known fixed sets of delta Ys. And if I look at like I have a number of these checks, basically a number of these directions, and for me to accept the image of the square root, this network has to behave in the correct way on all these directions delta x that I've chosen.
No, that's true. But look at the loss function. When you are training the system, you are considering all x very close to the image you are considering, say maybe font, right? But I'm talking about a scenario when I start with a natural image, not a zero image, but which is very, very different from x, and yes. I generate adversarial image so that it will get the same class level of x. That scenario is not taken care of through this loss function.
It is not, yeah. So, right. I mean, right. In a sense that, yeah, we don't take into account here whether or not the original is correct or not, like look for local consistency.
Yeah. Okay, thank you.
Yeah.
Okay, I had one question. So in the cryptography community, there's a long tradition of not doing security by obfuscation. The idea, prior to public key cryptography, people would just hide things like these fingerprints and so on, but those have been found to be very insecure. So you actually get some kind of guarantees by making some complexity theoretic assumptions like one-way functions. So so the method is disclosed, you disclose everything, and then you still guarantee security by hiding just your private keys or something where you secure them completely. Do you foresee that in the future this crypto philosophy will get incorporated here rather than sort of hiding these neural fingerprints? There will be actually some complexity theoretic guarantee of security?
That is really what I hope will happen. I think that basically, I think what I alluded to at the end is that really for us what we want is like a theoretical guarantee that we can, for instance, if we look at this image here, like we want some theoretical guarantee that once we go outside of the real data distribution, the attacker never can find any point where the fingerprint loss gets so low that we still might accept it as real. So that is, even if the attacker knows everything about my defense, knows the delta x's, knows the delta y's that I've chosen, like what I would like in that scenario is for us to have a theoretical guarantee that these real and fake images, so to say, can be properly separated by these chosen, by my choice of delta x's and delta y's. So I think the short answer is yes. I mean, I hope that some of that philosophy definitely will be relevant to this, business of trying to defend neural networks. Yeah.
Any other questions? Okay, let's thank the speaker again. So, Stephan, thanks very much. We know it's past your dinner time and you had a cold and so on. So we really appreciate your taking the effort to give us a very nice talk. Thanks and happy holidays.
Yeah, thank you, and enjoy the workshop there. Thank you so much.